वेलकम टू मैथ मंत्रा चैनल। आज हम लीनियर कॉन्ग्रुएंस का थर्ड पार्ट करेंगे, जिसमें थ्योरम नंबर 3 है। इट सेज इफ जीसीडी ऑफ ए एंड एम, दैट इज दिस जीसीडी ऑफ ए एंड एम इज इक्वल टू डी and d divides b, then the linear congruence ax is congruent to b modulo m has exactly d solutions which are incongruent modulo m। इसका प्रूफ 3 भागों में करेंगे। पहले उसमें प्रूव करेंगे कि इसके d solutions हैं, then we will prove that it has exactly d solutions, no more than d, and then these d solutions will be incongruent modulo m. So let's do the proof. Now the given congruence ax is congruent to b modulo m. As d divides b, therefore the congruence has a solution. Let it be x naught. Therefore, a x naught is congruent to b modulo m. Therefore, a x naught is congruent to b modulo m. Now subtracting 1 and 2, we get, subtracting 1 and 2, we get ax minus ax naught is congruent to 0 modulo m, and this implies m divides ax minus ax naught. That implies m divides a into x minus x naught. Now, as GCD of a and m is equal to d, therefore d divides a and d divides m. And this implies there exist a1 and m1 belongs to z, that is they are integer, where GCD of a1 and m1 is 1, that is they are co-prime, such that a is equal to a1d and m is equal to m1d. Let it be 3. Now putting the values of a and m in 3, we get a1d m1d divides a1d into x minus x naught. In this, d and d get cancelled. m1 divides a1 into x minus x naught. Now, since GCD of a1 and m1 is 1, therefore by Gauss theorem we get m1 divides x minus x naught, and this implies that x is congruent to x naught modulo m1, and this implies that x is equal to x naught plus k m1, where k is some integer. In this, thus we get the solutions x naught plus k m1. Let it be 4. Now put k is equal to 1, 0, 1, 2, so on up to d minus 1. We get thus we get the d solutions of the linear congruence Ax is congruent to B modulo M. D solutions are x naught plus m1, x naught plus 2 m1, so on to x naught plus d minus 1 m1. Now we shall prove that the solutions of 1 are exactly d. For this we will put k greater than or equal to d in 4. Here we will put k greater than or equal to d in 4, and we will see that the solutions so obtained are repeated and are one of the d solutions obtained in 5. Now, by division algorithm, k is equal to dp plus r, where p is an integer and r is less than d and greater than equal to 0. From 4 we get this 4 is x is equal to x naught plus k m1. X is equal to x naught plus the value of k, that is dp plus r, k m1, and that is equal to x naught plus d m1p plus r m1, that is equal to x naught plus r m1 plus mp, because m is equal to dm1, or x minus x naught plus r m1 is equal to mp, and this implies that m divides x minus x naught plus r m1 by definition of congruence and by definition of congruence. We get x is congruent to x naught plus r m1 modulo m, where 0 is less than or equal to r is less than or equal to d minus 1. Which is one of the solutions obtained in the set 5. Thus, we have proved that there are exactly D solutions. So it remains to prove that that is the D solutions are incongruent modulo M. For this, if possible, let x0 plus m1 k1 is congruent to x0 plus m1 k2 modulo M, where 0 is less than equal to k1, k2 is less than equal to d minus 1. Means k1 and k2 both are greater than equal to 0 and less than equal to d minus 1. And k1 is not equal to k2. Also k1 is not equal to k2. Therefore, from here we can say that M divides this difference, that is x0 plus m1 k1 minus x0 minus m1 k2. And this implies M divides this x0 and x0 cancels. So m1 k1 minus m1 k2. And this implies M divides m1 into k1 minus k2. And this implies m1d divides m1 into k1 minus k2, because m is equal to m1d. And this implies this m1 get cancelled, so d divides k1 minus k2. But as we know that mod of k1 minus k2 must be less than d, therefore k1 minus k2 must be equal to 0. And this implies k1 is equal to k2, which is contradiction to our assumption. Therefore, x0 plus m1 k1 is incongruent x0 plus m1 k2 modulo M, where k1, k2 are less than equal to d minus 1 and greater than equal to 0. Therefore, x0 plus m1 k1 is incongruent x0 plus m1 k2 modulo M, where k1, k2 lies between 0 and d minus 1. Hence, we can say, hence the theorem is proved.